The FKI Tower is a competition we won in the spring of 2009. It was an invited competition to design a new headquarters building for the Federation of Korean Industries. They're a trade group that represents the major industries in Korea, and they had an existing building here from about 40, 50 years ago. They had outlived this new life, and instead of remodeling as the UN decided to do, they chose to tear it down and build a new building on the site. We won the competition for this very kind of traditional modernist office building. The client was really looking for a 50-story rectangular 3-zone office building where function was the primary component. Function was the primary thing they were looking for. And we also had to meet, which became the interesting portion of this project, a requirement by the city of Seoul that 5% of its energy had to be generated on site. So this became the challenge and the design possibilities for us, and we moved on from here. So you can see the building's about 244 meters tall, 50 stories is about 2,400 square meters of floor plate, very traditional. But we also have this podium building, which is the second component. So we have the tower, and then the podium building is the second design element. It's a 3-story conference center. The client had a smaller version on the site, but they want to kind of expand that and develop that. And we created this balance between the large kind of rectangular traditional office building and the more kind of formal exploration of the podium. So the project became all about this kind of sustainable goals and how to meet that 5% or go higher above that. So you can see it meets LEED Gold in Korea. The tower generates enough power to generate 274 households, power 274 households, and reduce emissions of 374 tons per year. It's about 2,110 kilowatts a day or 700 megawatts a year. It generates about 25% of the building's energy use and reduces 31% of the overall energy cost. The VIPVs, which we'll talk about mostly, generate about 20% of the total overall lighting and about 7% of the overall tower's energy. And out of the other parking spaces in the tower, about 32 of them are electric cars, which is actually 9% of the total electrical cars, power stations in Seoul. So that's not saying much for Seoul, but it's saying a lot for the client. And you can see some of the other kind of features here. We have on the floor air distribution, we have great water recycling, geothermal is about 10% of the building's energy consumption is generated from the geothermal systems. So it's an overall system component, but we spent the majority of the work was done on the facade and developing the facade for this building that will kind of begin to explain what we're trying to achieve. How does Adrian Smith Gill do a traditional 50-story modernist office building? What does that mean to us? And how do we reinterpret that going forward? So you can see where the building is located here in Seoul. If you know Seoul a bit, it's located in Yeouido Island. So it's across, this is the government center, government area, and all the high-rise buildings are going up on this side of the island. The old city is across the way. And one of the major planning requirements we had is that the building had to be rectilinear to the grid. We couldn't rotate it, which was something we'll talk about in a minute. So you can see how it sits right on the main avenue, right in the main park. It's the main public space in Seoul within the business district. And that was a given that we couldn't move away from. So 2 components, as mentioned, is the tower and the podium building. And we're going to focus on the tower today, just kind of talk about its energies and its ideas. But I want to show a few pictures of the podium building, which we can spend a whole other day talking about. We try to do this kind of combination. So the tower is very simple. We wanted a very rectilinear functional building, but we had a lot more freedom with the podium. And our client it was great when it came to the podium building. They bought it from day one. They bought into it. They loved it. They couldn't let it go. There was days they couldn't afford it. There was days that we couldn't make it function. There was days that we couldn't get the glass on site, but they stuck through it all the way through. And you can see some of the renderings here. And then here's the building completed. And they built it. They really came all the way through with this building, and they loved it. They believed in it. And sometimes we couldn't see it happening. But here's some of the spaces inside that podium building. It's a complex compound shape. We spend a lot of time as a ballroom, conference centers. In Korean culture, a lot of the weddings happening here. So the chairman's the first wedding inside the building was actually the chairman's daughter. So it's been booked since day one. They don't have any time open. And you can see some of the images inside the space. So the towers we want to focus on it. Like I said, it's a 50-story rectilinear kind of very classic modernist building. And we took some advantages with that and tried to find things to look for. The first one really had to be how we looked at the plan and how we thought about the idea of bringing bringing public space up into the building, which we look at all floors and we look at the roof as well. And we started looking at, you can see very clearly, a 9-meter grid, traditional office, 3-zone building, this idea of these atrium spaces, which begin to populate the building. We kind of begin to break the mass down. So the mass is irregular and create these volumes to float throughout the building. And how those begin to be accessible by the public or by the users of the building. So you don't have to go outside necessarily to be able to find some open space within your building. So every floor has access directly to one of these spaces or views into it. They're 3-story atriums. And you can see some of the views. There's a rendering on the right side and one of the finished photos from inside of the atrium. Great views, clear glass all out. Here's a space, here's a completed space. It's a 3-story atrium. Every floor has access to one of these, or views into one of these. They're kind of become almost smoking balconies at this point. This is one of the pictures that was taken right at the end of construction. So they're now been populated with furniture and people sitting out here. Last time I was there was people all over these. So they're being well received. The structural system done by Thorman Tomasetti, who's our structural engineer, and ESD here was our mechanical engineer. It's a composite system, core, outriggers, belt trusses at the 2 mechanical floors, and the traditional column system on the perimeter. So when we start looking at the facade, we get this brief, we look at the competition, and says, okay, you have to generate 5% of the energy inside. How do we do that? And they gave us a set of restrictions of what energy types we can generate. So the first one is, okay, VIPV became a very simple, easy way to get to this point. And how does that become a design catalyst for us? How do we design this building from the facade as a skin, as a new skin for us, and how does that become the catalyst? How do we optimize it? How do we balance it, make sure this thing's working correctly? And how do we integrate it? Comfort, issues of those systems. So those became the 3 concepts that we looked at, and we'll talk about some more. The first one, the concept as a VIP is like a design catalyst. So how do we decide it? Design constraints are a main issue. How do we begin to deal with the building orientation and the context around us? Power generation requirements, meeting the city's basic requirements for 5%. And the incentives. So what was great about the projects is that it wouldn't work from a financial perspective so unless the city had an incentive, a buyback. So with the energy we're generating is sold or we're getting credits. It changed in the middle of the project from being sold back to the power station or instead of getting credit. So that made it feasible. It went from being 5% that was generated when you're actually getting, the return was about 5 to 1 when they were paying 5 times as much as we were generating. So it made it doable for the client. So as I mentioned, we couldn't rotate the building. The building had to be rectilinear, but the grid is not actually north-south grid, so we're not getting direct exposures off tilt. But you can see we're sitting on the site here across the park. And we started looking at how much daylighting, and you can see the building's rotation to north-south. So we're not putting our broad face to the south, which is what we wanted to do from an energy perspective. So, okay, how does that deal with it, and what kind of weather information we get? Weather data is something that's, if you ever visit our office, it's just everywhere. And we're continuously looking at the weather data, what's going on, how much energy are we getting on site, how many sunny days, how many cloudy days, how can we use this information to further the design of the building? And then the power generation requirements. So the city came out and said, well, you can use geothermal, solar, wind, fuel cell, and the hydro. We realized pretty early on that wind was not going to do much for us. Fuel cells was a cost issue in hydro, so geothermal and solar became the primary components, and solar being the primary component from an architectural perspective. So as we started looking at the massing of the building, 2 specific areas, the facade, the spandrel panels. We have about 16,000 square meters of spandrel panels, great area for photovoltaics. And then the roof is unobstructed. We have about 2,000 square meters worth of space on the roof that we can completely populate with photovoltaics. So those 2 areas were isolated and understood, and then we kind of did an area calculation, understand how many cells we can get on the roof, how many cells we can get on the wall, added that up, and kind of got that basic number. So the numbers we begin to work with, the numbers that we're generating internally with the engineers. And since, to Jeannie's point, actually, we spend a lot of time actually with our client. We're getting feedback from the building on a regular basis. So the numbers that we've had continue to be tweaked and understood based on the data we're getting back from the building. And that's something important to us as we develop the next generation of these buildings. What can we do different to actually improve this? What worked, what didn't work? How are the numbers, why are these numbers not what we thought they would be? Where are they better, where they're not better? So that's an important key to developing any of these buildings. And the incentives, the renewable incentives, right? So we're getting these RECs, right? Renewable energy credits. So 1 credit equals 1 megawatt of renewable energy. So you can begin to see the metrics. that incentive, that getting much more than you're paying back. So I make 5% on site, but if I sell it on 124, I'm actually almost making 20% on site when you get the money back from the energy company. So that really made it work, and it made, it's an incentive that's making a lot of buildings in Seoul be able to do this. And you can see here, as you begin to add the credits and you turn it into money, it's about, the total energy savings is about 6.9%, and there's a cost savings of 5.3%, which is a lot of money for an office building as it begins to generate it. So if it's 5%, but you multiply it times 20, that's a great amount, but you begin to say, okay, what is that as a percentage of the building's basic light systems? So not powering computers, not powering anything, but elevators, exit lighting, it becomes a much larger numbers in the 30%. So now you're generating a lot of power by being able to sell it back at a different rate. So it actually begins to make a big difference. And we're going to look at some basic paybacks. You can see at the bottom, BIPB with the REX, the payback, total payback, some different chart, but it was about 7 years what I came out to at the end. And then, you know, the systems, everything we use, everything we did, you can see the basic base, the Atrium base standard on the left. And as we move back across the building, everything that we did to the glazing, the U values, the lighting power, the chillers, all the systems begin to help us reduce and bring the power consumption down within the building. So optimizing, how do we do this? How do we get this building to do more than one thing, which is what actually became the most interesting part, the multitasking. The balance between performance and human comfort, this is a client issue. And architectural expression, what does that mean from an architectural expression? The multitasking, glare reduction, shading. So when we started looking at the building, we said, okay, the first thing, there's 3 diagrams, yeah. So the PV, it wants to be at an angle from the facade, right? You got your typical flat facade, but we want to angle that PV out. Probably at 30 degrees would be the best thing you can do. We know that that's probably the best angle, but we know if we go over above a 15-degree tilt on the glass, we have an overhead condition, and now you got a set of different code issues to deal with. So we said, okay, 15 degrees is really what you want to go the most tilt that you actually want to have on this building without getting into a whole set of issues. So by angling the sun, by angling out to the sun 15 degrees, we begin to improve the quality of the PV from having it flat on the spandrel. The other thing that we're doing is we begin to balance and some of the glare. So the glare is not coming straight into the building by that angle. It's helping us reduce glare. And the third thing that we learned as we're going to do this is that we're reducing solar gain heats, right? We're self-shading the building, right? So angling the facade, the actual vision aspect of the facade is tilting down. So in the summer, you're shading yourself. And how do we begin to balance that with human comfort? So we'll look at both of those as well. So we knew that 15% was the max, but our client was having some issues with the idea of this tilted glass. I don't know if it can be a leasable problem, people comfort, perception, how do you walk up to it, how does that feel, is there reflections at night? So we looked at a bunch of different expressions for the facade. We looked at a 5%, a 10%, and the 15%, which we felt was kind of the best performance from the PV perspective, but not from a comfort perspective. And then we worked with ESD to generate these 2 charts, which are actually probably the most important charts in the whole presentation. The one on the left is the effect of the wall tilt on heating and cooling. So obviously, as I tilt further out, it's helping me with the cooling loads because I'm shading, but I'm also shading, so it's hurting me in the winter. Now I'm shading in the winter when I want to let the sun in. So you can begin to see here in that chart on the left, heating going up, cooling going down, and then that sweet spot, somewhere about 13 degrees, 12.5 degrees for this kind of latitude, where the right balance between how much heating you're letting in, how much cooling you're letting in the winter. And on the left, on the chart on the right side, is the effect of the wall tilt on the surface solar radiation. And it's pretty much the same thing. And you can see they both end up somewhere around 13 degrees is the sweet spot from heating and cooling. Knowing the PV is the best is the 15, we're tilting toward leaning it towards the 15 degree, which is what we were recommending to the client. They were still not sure about it, so we did a lot of renderings. We looked at the 10 degree, the 15 degree angles. We played a lot with that. And then what they actually did is they hired a current wall manufacturer pretty early on who was able to make a mock-up, an adjustable mock-up. You can see these brackets up here. We got our client out, and they got up there, and they were tilting it down and looking at it, and they couldn't make a decision. So it went all the way through the DD process until we got to the end, and they asked us what we thought. The chairman came down and said 15 degrees. So we moved forward with 15 degrees. You can see the final pictures here of what it was actually built. Mock-ups, a lot of study mock-ups, performance mock-ups, test mock-ups, visual mock-ups. And then how do we integrate that into the building for the BEP, for the wall, and for the roof systems, the location? So this is the final outcome with the operable panels on the building. And we did a lot of solar studies. What is the angles of this? Where is the PV? A lot of ecotech analysis, understanding due to the angle of the building, we can't locate that building straight north-south. So we know that looking at the chart, this green area, we get a lot of bounds, and then we get an adjacent building. So we know the southeast and the southwest facades are probably the only two which are getting enough direct radiation to be able to make this work. And we looked at it for both solar radiation and total radiation. And then we came up with that facade, that 15-degree. We spent a lot of time detailing it, understanding the panel size. How does that panel, it's a 4.5 meter floor to floor with a 3 meter wide panel. How does that come to the site? How is it being installed? How is it being powered and so how many cells are we actually going to generate? What does that cell begin to look like? We work with the manufacturers to get a mock-up of that done and begin to look at all the deal. Where's that power going to? We were originally trying to let some of that heat come back out, but we realized there was going to be snow and ice buildup, so we had to take some of the heat back through the slab, up below the slab in the return slots with the rest of the air. And on the roof system, what was great about the roof system is that we didn't have an angle problem. We would have turned that PV directly facing south. So as the building's not facing south, we said that PV can go straight south, no problems, we'll rotate it, but we have a finite amount of space. So it became a balance. Okay, if you look at PVs on the field somewhere, they're spaced out pretty far apart, so you can get the maximum angle, you can get no shade in between them, they're not shadowing each other. So it became a balance of how many PVs can I fit on the roof, what's the spacing, and what's the best angle for that. Trying to balance those three things so we can generate as much energy as possible. So we tied them a little tighter, lower the angle so they're not shading each other so we can maximize the energy production on the roof. And then what we did on the north side, we put a clear light, skylight, to let some of the light into that roof garden. So once again, we went back to ecotech, did all of our analysis. We looked at the performance of the building, how much shadow it was creating on itself. And then we had an issue with the site trying to generate enough green space on site. We had a problem that we were not generating enough green area because we had the big podium building that didn't have before. So a solution came that we can put a roof garden on the top of this building and that will count towards green areas. So we said, great. How do we do that when we have this PV on top of it? How can we actually fix this problem? So great, simple solution. This is the panels on the enclosed on the restaurant side. These are the panels on the roof garden side. We just removed the glass on the north face. So the ones on the garden don't have an enclosed light, and that made it an outdoor space, and we were able to meet our green area requirements. So you can see here kind of two construction photos. When you're looking at it from the south, you see the skylight and the clear light, so you can get a lot of natural light looking out. When you look at it from the north side, all you see is really the PVs on the roof space. So it gives you two very different qualities to the space as you begin to look at the building from either side. And then here's some of the roof garden spaces. So this is they can't get, this space, they have to now control access to the roof garden because there's so many people trying to get up there from the building. So we created this pretty large roof garden. It's about 1,500 square meters worth of green area on the roof, 50 stories above ground. And we're getting these kind of unexpected, beautiful shadows and light play from the photovoltaics as they're reflecting into the wall. And you can see some of the finished construction photos here. So yeah, it's about 2-story space, outdoor space. This actually doesn't have any glass on this side, so the outdoor space is being drained. This is a set of restaurants that we have a connection to below. And this is kind of the final photo of the building. So we're pretty happy with the results. We think it's a great example of what we're trying to do with this building typology. How do we take this building forward? And we're trying to learn from it as much as we can. Thank you.